Okay, so shall I share my
I think Christina has to stop the sharing.
I think I did already. I hope I did.
Okay.
So then you should try.
So let's share. Okay, I'm almost done. Can you see my screen?
Yes.
Okay, I will put full screen. All right. So let me just set.
Perfect.
Okay, can I start then?
Yes, please.
Okay. So good afternoon, everybody. It's a pleasure to be here. My name is Nicolás Cuello. I'm working at the IPAG in Grenoble, France. And today I'm going to talk about the ongoing flyby in the young multiple system UX Tauri. So this is the outlook of this talk. I will briefly summarize the dynamical and observational signatures of stellar flybys. Then I will talk in detail about the multiple system UX Tauri. And then I will show a few flyby candidates and briefly discuss the implications for planet formation. And I would like to thank all the collaborators that participated to create all this work I'm going to present. So they're listed here. And so they were really key to understand and put this picture together. So if we want to summarize what is the effect of stellar flybys on disks, first we need to start with a definition. So it's an interaction between two or more stars where one of the participants has an eccentricity larger than 1, and it has to come to a reasonable distance, let's say between 100 and 1,000 AU, in order to create a dynamical signature without being too destructive. And this kind of flybys occur because of the chaotic nature of the process of star formation, or also because the hierarchical decay in multiple systems. So examples of this can be seen in the simulations of Matthew Bate, or the work, for example, done by Bo Rayporth and Nicola. And one can estimate what's the probability of such an encounter, or how much time it takes to have an encounter of this kind. And it's inversely proportional to the stellar density, and also to the stellar mass of the perturber, as you can see here in this equation. And one can also try to think what's a probable perturber in a given distribution. That's an exercise that was done by Susan Fassner, and you can find that, for example, a parabolic encounter with eccentricity close to 1, it's likely, and you have more probabilities to have an encounter with a low mass star below 1 solar mass. And you can also see that the probability for these encounters changes with the stellar environment. This is something that Andrew Winter and collaborators looked a couple of years ago. And if you take, for example, a minimum distance of 300 AU and a fairly dense environment, you find that the probability of experiencing an encounter after 3 million years is between 10 and 100%. So the takeaway message here is that flybys occur in young regions of high stellar density. So for the dynamical signatures, I'm going to go very quick here. We have spirals, as one should expect. Here I'm showing an example on the right. So this is a face-on view of an encounter. It's a prograde and inclined encounter. So you can see like two prominent spirals. You see here in the edge-on view that this is highly non-coplanar. There is also the fact that the disk is truncated after the encounter, and that during the encounter we can generate warps or even inclined the disk. This is especially true for inclined retrograde encounters. And lastly, we have accretion events, because when we shake the disk, we can excite the disk in such a way that generates a mass inflow, which translates into a luminosity outburst. So I left here several relevant references for this. And what we did a year ago, mainly with Giovanni Di Piero, was to check how the dust would be trapped in these asymmetric structures. So here you can see that the dust is trapped in very different ways depending on the degree of coupling with the gas. So here you have from 1 micron to 10 centimeter particles, and you can see, for example, that the 1 millimeter particles are very well trapped inside the spirals, and that we also have an important radial drift. And these kind of structures strongly depend on the different type of stellar flybys. So this is just an example of an inclined and prograde flyby as the one before. The main message here is that we can connect the flyby orbit with the disk morphology that results from the encounter. And there are some open questions about the planetesimal formation. Do the flybys speed up or prevent the process of planet formation? That's something to think about. And then using those simulations, we construct a realistic disk model, which allowed us to do synthetic observations. So here you have the example I just showed for a sphere-like observation and moment 1 and moment 0 ALMA maps here on the middle and on the right. And you can hear here the continuum lines this is the continuum emission from the millimetric dust, let's say. And here you see the edge-on view of this system. And what we can notice is that there are mainly 3 things. You have spirals in scattered light that can be interpreted as gaseous bridges. Then we have the compact emission in the continuum compared to the gas. And then we also have non-coplanar structure in the CO emission lines, so like warps and inclined disks. And we can see this in the individual channel map. This is very interesting. But we need to put the flybys in the context and in the environment. So if our working hypothesis is that the flybys preferentially occur in regions of high stellar density, then it should be a link between flybys and the stellar environment. This is the exercise that Isabelle Joncourt did here. And I'm just showing a couple of examples like RW Riga, which was proposed as a flyby by Dai et al. And so here's the hydro modeling, and the HV tau and do tau by Andrew Winter and collaborators. And we can try to connect this with the stellar nests that are nearby. This does not really work in this case for RW Riga, perhaps for HV tau and do tau. So we could think about hierarchical decay of multiple systems or even random encounters. But now let's go to UX Tau. This is the system we're interested in. It's a quadruple system. You can see 4 stars, a binary UX Tau B, sorry, on the right. This is the primary UX Tau A and UX Tau C. This is going to be the perturber in this case. And the projected separation between these 2 stars given the distance is 400 AU. And we published this earlier this year. And what we can see is that if we combine J and H bands and we push the contrast to the very limit, we can see 2 very prominent spiral arms around the primary. And here you have the continuum emission seen with ALMA. And here is the perturber. Okay, so we need to understand what's going on here. For that, we did a series of simulations taking into account a bound companion, so an outer binary, let's call it, and an unbound companion, so a flyby. And what we realized is that it's very hard to create these prominent spiral arms with a bound companion, because after a few orbits, we eject all the material and there is no more material available to only as the one shown here. So if we zoom, this is the observation with sphere, and this is the hydro modeling we're proposing with the parameters here. And it works fairly well. So that's what lands support on our hypothesis of a stellar flyby here. And another interesting thing is that we discovered for the very first time the disk around C in scattered light. This disk is also seen in CO, as you can see. So here is the system, the total system. Here's UX Tau C. You can see that the disk is seen here. And another interesting thing is that we do not see continuum emission here. The continuum emission only comes from here, as you can see in the zoom. And these 2 disks are misaligned between each other. So this is a very interesting fact, because also it suggests that this encounter happened in a non-coplanar fashion. So we have this idea that perhaps the disk was captured during the encounter. So for that to happen, you need to have a phase of radial drift at the very beginning. Then you make the flyby, and C captures the outer parts of the disk, which are mainly micron-sized dust or gas. And that's why perhaps we only see this only in the gas or in the scatter light. So in order to validate this, we need further simulations with gas and dust modeling, but it seems promising. And another idea is that perhaps the C perturber here was ejected from the binary B, which is to the west here. Well, I would also like to advertise a denoising tool that Daniel Price created during this project. So here you have, as an example, the J band, the polarized intensity in J band. Here you have the denoised image from here. And then here on the right, we have image before combining them when we do polarized differential imaging. And this gives very nice results. And it's a fast and cheap way to recover hidden signal close to the noise level. So I encourage you to try. This is available in Splash. And if you want more information, please read the Appendix C in Ménard et al. 2020. And lastly, here are some more flyby-shaped disks. So we have SR24, AS205, and Z Canis Majoris on the right. So these observations are, so these are all multiple systems. There are at least 2 stars. And the common point is that you can see that there is a lot of stars. And so if we go to an updated version of these observations, you can see here, for example, for SR24, that there is a lot of material. So this is an HST image, and you can see the continuum in there, and you see that there is a kind of a spiral connecting, or a gaseous bridge connecting both stars, which suggests interaction. Then in the center, before you had the observation by Nicolás Cuello and collaborators and the CO moment zero map, and here we have the scattered the light image seen with SPHERE. So this is unpublished, so please do not share it. While we can see that there is material in between, that there seems to be spiral-like shapes all over the place, and we are already modeling this source. And on the very right, you can see that this disk, where you have this very prominent spiral or tidal tail, you can see that here there is a binary, but we discovered that there is a point source here, which seems to be connected to this system. So stay tuned, because we're working on this with Robin Dong and collaborators. And the interesting thing is that all these systems are triple stellar systems and seem to be in hierarchical configuration. So the following question is this hierarchical ejection, or is a random encounter? And the interesting thing is that flybys are able to reproduce the disk morphology, although we all know that flybys should be not very likely. We seem to be witnessing many of them. So to conclude, we can connect the flyby parameters to the resulting disk morphology. In particular, it's important to consider the orbital inclination, for example, prograde or retrograde, the mass ratio between the stars, and the ratio between the size of the disk and the distance of minimum approach of pericentre. Then the multi-wavelength observations are key to reconstruct these scenarios of interaction, and bound to fail here most of the time. And for UX Tau, we have an ongoing prograde and inclined flyby. And we discovered for the first time these gaseous spirals with SPHERE and ALMA. And there is this idea about the captured material around the star C. And some things that we could discuss during this workshop is the connection with the FU Orionis events, the effects on planetesimal formation, and lastly, the resulting planetary architectures on this. With this, I conclude, and thank you very much for your attention.
You were perfect on time. That was a noise right now. Thanks a lot, Nicolás. Yes, we have a question here in the chat. A question from Mario. It is about the accretion burst triggered by close encounters. I'd like to know how the duration of the accretion burst and the time when it starts compares with the time scale of the gravitational interaction.
Yes, so this is something we measured when we did this work here with Giovanni Di Piero. We measured the accretion rate on the primary star when you have this encounter. And we realized that the moment at which you have the maximum accretion into the primary is a bit after you go through the pericentre. And in order to have a lot of accretion, this needs to be prograde and a prograde encounter, as expected from theoretical estimates. And the burst can be pretty significant, but it's of course it's degenerate as a problem. The closer you get, or the more massive you are, the higher the burst. But you can increase the mass accretion by a factor of 10 or even 100 if you want, being realistic. And then the problem is that this it gets some time to reach the peak, and then it goes down in a few hundred years.
And let me see. There's a question from Stefano. Stefano Faccini.
Yeah. Hey, Nicolás. So I have two related quick questions. The first one is, in UX Tau, can you say whether the actual gas spiral is unbound from the ALMA kinematics from the primary? And the second question is, how can you distinguish between an unbound system and a bound system with a very high, like 0.98 eccentricity on a very long dynamical timescale?
Well, regarding the first one, I think really have, a strong. Can you see my?
Yeah, I can.
Okay. So I think we have a clear disk structure around this and around this point here. Regarding the material here, I wouldn't know how connected or bound is to the. That's a good point. I don't know.
No, because I think we did on RWA rig, and we can see that just the line of sight velocity is just higher than the escape velocity from the system. I was just thinking maybe you could have a quick look, because that can help with understanding if the other star is bound or not also.
Okay, cool. Yeah. I think there is also this work by Luis Zapata and collaborators where they looked carefully to the kinematics. I should check that work as well. And regarding the second question, we tried fairly high eccentricities, such as this one. And as you said, we could have a very, very high eccentricity and almost have a flyby-like encounter. This could reproduce these observations, but only 2 or 3 orbits. After that, when you do like the fourth encounter, you don't have enough material close. In these regions, it's very depleted, so you don't see anything. So that was our main evidence in favor of flybys. But yes, of course, a bound companion on a very eccentric orbit and that passes a couple of times, that works as well.
Yeah, thanks.
Okay, the next question was, I think, from Miriam Benesti, and her question is related to the accretion burst triggering. And she's asking, how does it compare to UX Tauri outburst durations versus FU-Tauri outburst durations?
That's a good point. I'm not really sure how. I don't have the numbers on top of my head for UX Tauri. I'm not sure there is an ongoing high accretion burst. Perhaps she can give me some information on this. What I know that in FU-Tauri, it's a very strong, in the matter of 1 year kind of time scale. You have a jump, a very strong high jump in accretion, and then it goes down very slowly. We can reproduce that jump, but not the time scale. That's something that only the flyby, as we consider it, it's the dynamical time scale is a bit longer than that. So we need to think about other scenarios. As there are some scenarios proposed about how you can trigger such an accretion.
Okay, then we have one question from Cassie Clark.
Yeah, I was just interested on the question of the time lapse between the triggering of the outer disk and the accretion burst on the star. In your models, how does that depend on the viscosity in your disk? And can you actually use it to measure viscosity even?
So I must say that in these simulations we did a couple of years ago, we did not change much the viscosity, so we did not play with that parameter. But yes, in principle, it should depend on the viscosity, and it could be a way to measure the disk viscosity. The problem again is that it's very degenerate as a problem, and so what we found, and as expected, is that prograde encounters were very good at delivering material onto the primary, especially if it's a bit inclined. And but we didn't check carefully how this changes with viscosity. That's a good point.
Thanks.
Thank you.
And the last question from Susanne.
We found quite a number of cases where you can see now the effect of a flyby, but these features probably don't last endlessly. So they're probably the tip of the iceberg of how many encounters happen. Do you have estimated backwards, basically, how many close encounters there should be?
Oh, yeah, I haven't done this exercise. I mostly relied on the work done on n-body simulations as the ones you did and the ones that Andrew Winter did. But I for sure think that dynamical encounters, if we're seeing so many, they should have played a major role in previously. So the fact that we're seeing, for example, in this ALMA survey is very small disks, because there is a very strong bias towards the brighter guys and the more massive guys. But there is also a whole population of very small guys or disks, which might be the result of dynamical encounters in the very early phases. But I haven't estimated how many of them. But I think it's definitely important, the dynamical interaction at the very early stages.
Okay, thanks. And with this, we close the first part of